Hello, everybody. Today I wanted to talk about the difference between physics and math because to many people, these two fields are the exact same, or it's very hard to distinguish what these two fields are. And really, the reason why I wanted to talk about this is because when I was in high school and I was trying to figure out what field of study I wanted to pursue in my post secondary career, well, I just thought, yeah, I'll study physics and math. It's like in my mind it was the same thing. I didn't really know what the difference was. But of course, like, there is a difference. I mean, we have a word physics and we have a word math. They're not the same word, so clearly there must lie a difference somewhere. And I discovered this as I was progressing in my university career that these two things they're different. Um I mean, yeah, they're different, and I actually ended up preferring math and I switched into the math stream. But so let me break down what the difference really is, because there's a fundamental difference. Even though these two fields of study they share the same language essentially. I mean, they both talk with math, um, since they share the same language, but kind of, I guess you could say, the apparatus that the apparatus that uses this language in both instances are fundamentally different. And the fundamental difference here is that physics is a science and math is some weird kid. I don't know. Math is a little bit unique in that sense, where the axiomatic approach that math takes is kind of, well, unique to the field itself, as far as I know. So let me break that down a little bit more. So, scientific approach in physics, what is that? The scientific approach, the way it works is essentially one posits a hypothesis or a theory, and this hypothesis or theory can never be validated. It can only be disproven. But the theories that we consider to be quote unquote true are theories that have stood the testament of time, and that when people have done experiments to try and disprove these theories have remained unscathed. And so that's kind of the way the scientific process works. And physics depends on this. So that is to say, if we see an inconsistency between the data that we collected experimentally and what our theoretical knowledge posits, if we see that there's exactly that, a discrepancy, then we have to rectify that discrepancy some way, somehow. But math is different. The way math works is that it depends on what we call axioms, the axiomatic approach to the acquisition of knowledge. And so in math, we'll say there's a set of presuppositions that are irreducible and that are fundamental. And then from this set, say a set of four, it could be five or whatever, an arbitrary number, but we want to make the set as small as possible. And so we take this set and we want to prove everything that we know from this set. And one example of this that you might learn as you study math, if you choose to study math or if you're already studying math, is that the number zero is unique. There's only one zero. That is to say, if I add zero to any number, let's say a, then it'll give me a. So like 0 plus a is a. But there's only one element that does this in the numbers that we know. And in fact, this is not an axiom. This is not something that we have supposed. It's not something that we just assume to be true. We've proved this from a set of axioms. So we start with a set of axioms and then we proved the unicity, the uniqueness of the element zero. And so that's kind of the way they work, where math doesn't really, I mean, math can sometimes not really be grounded in reality, insofar that the axioms can be whatever we choose, and we play around with what different axioms mean for our mathematical structures. But of course, math does have some relevance. It is born, I guess you could say, of the physical world. In fact, a lot of physics motivates a generation of math, um, because a lot of axioms have to, well, they don't have to, but the way we've done is the axioms match closely what we've observed in our life. But they don't really depend on the scientific process to say, oh yeah, if these axioms are true or not. And so really that is the difference between math and physics. And maybe this video would be helpful to those trying to decide what they want to study, as I had. But practically speaking, the difference between math is perhaps not as great as their difference philosophically or fundamentally, in their approach to the acquisition of knowledge. But the thing is, math and physics practically are very similar. I mean, a lot of math, when you study math, can be applied. Like, it's applied math. For example, physics is one example of where math is applied, and we can see this in other fields too, like chemistry or biology. And so maybe practically this video isn't really useful, but if you are more interested in the philosophy behind these types of things, then maybe this is an interesting discussion. So, well, yeah, essentially that's the difference between the two. I think it's pretty cool that even though these two fields are very similar, they are in fact not the same. They have completely different natures. So, I mean, that's basically it. Thank you for watching.